Welcome to the Non-Destructive Testing and Evaluation course. The course code is ME8097 for the regulation 2017. So in this video session, we'll be studying about the acoustic emission testing of Unit 4. So we'll be studying about in ultrasonic testing, we'll be studying about the ultrasonic testing principles, the transducers, transmissions, and pulse echo method, straight beam and angle beam method, instrumentations, the data representation like A scan, B scan, C scan, phased array ultrasound, time of light diffraction, acoustic emission techniques, its principles, acoustic emission parameters, and industrial application of ultrasonic testing and acoustic emission testing. So in this video session, we'll be studying about the acoustic emission techniques, its principles, parameters, and its industrial applications, advantages, disadvantages, and so coming to the introduction of acoustic emission. So here the acoustic emission may be defined as a transient elastic wave, which is generated by the rapid release of energy within the material. So here you have the structure. This is a structure. When it is subject to an external stimulus, that is a change in pressure, load, or temperature, and localized sources trigger and release some kind of energy, that is in the form of stress waves. So this will propagate to the surface and are recorded by the sensors. So this occurs when the small surface displacement of material is produced. This is a way how this acoustic emission waves are emitted and it's been sensed by the sensors, and from which you can find out the defects of the test specimen. So coming to the history and facts, the first practical use of acoustic emission was by pottery makers, and as early as 6500 BC, these potters were known to listen for audible sounds during the cooling of the ceramics in order to assess the quality of the product. And the first observation probably of this acoustic emission in metal was during twinning of pure tin as early as 3700 BC. And the first documented observation of acoustic emission appeared to have been made in the 8th century by Arabian alchemist Jabir ibn Ayyub. So he described the harsh sound or crashing noise emitted from tin. And he also described iron as sounding much during forging. And in the year 1936, this Frederick Foster and Verick Seychelles, Germany, conducted experiments that measured that small voltage and resistance variations which caused by the sudden strain movements. It was caused by the Martinistic transformation. And now, today, acoustic emission, it's one of the non-destructive testing used practically in all industries all around the world for different types of materials and structures. So this is the testing process. And here you have this is the test specimen, and you have a sensor above the test specimen. And this test specimen, which is subjected to an external stimulus, and as energy is released, acoustic emission waves are released from the test specimen where there is the defects, and this emitted acoustic waves is sensed by the sensor, and this acoustic waves are transmitted as a signal, and it's converted into pulse form by the circuitry unit and is being displayed on the screen as an image, as a signal. And thus the defects in the test specimen can be identified in the stress material. So detection of acoustic emission. So the source of acoustic emission may include many different mechanisms or deformations and fracture, while detecting the detection process remains the same. And here, as the cracks grows, a number of emissions are released, and this emitted acoustic emitted waves arrives at the surface of the test specimen. You can see it as right on the surface of the test specimen. A minute movement of the surface molecules occur, and this sensors will capture this acoustic emitted waves and the mechanical movement, detect this mechanical movement and convert into usable electrical signals, and that will be supplied, transmitted to the circuitry unit, and will be displayed on the CRT monitor as a signal. So processing of acoustic emission signal. So this small voltage generated by the sensor will be amplified, and the raw radio frequency signal is transferred to the computer. And this, based on the user-defined characteristics, this radio frequency signal is split into discrete waveforms. And these waveforms are then prescribed by the characteristics such as amplitude, rise time, absolute energy, and it's all based on the user-defined threshold. So this is displaying acoustic emission signal. And this collected waveforms can be displayed in two ways. So one, function of waveform parameters, and two, as the collected waveform itself. So most of the acoustic emission tests currently only record the waveform parameters, and it ignores the collected waveform, mainly due to the large amount of computing memory in its uses. So locating acoustic emission signals. And this automated source location capability of acoustic emission is perhaps the most significant attraction as a non-destructive testing techniques. And here the predominant method of the source location is based on the measurement of the difference in time between the arrival of acoustic emission signals at different sensors in array. Here you can see two sensors are placed in array on above the test specimens, and the emitted acoustic emitted waves from the cracks is being sensed by the sensor present in the so different form other than non-destructive testing techniques. So this acoustic emission technique is most different from other non-destructive testing techniques. So the first difference pertains to origin of the signal, and the second difference is that acoustic emission testing deals with dynamic process or changes in the material. And here the instrumentation, typical acoustic emission instrument consists of the following components. It will have a sensor used to detect acoustic emission events, which senses the emitted acoustic emission waves, and it has a pre-amplifier unit, amplifies the initial signal, and the typical amplification gain is 40 or 60 dB, and you have cables which transfer signals on distances up to 200 meters to the acoustic emission devices. And the cable used here are mostly of coaxial type, and the data acquisition device which performs filtration, signals, parameters evaluation, and data analysis, and the charts is being prepared. And sensors. So the acoustic emission sensors with amazing sensitivity to motion in the low ultrasonic frequency range, that is 10 kilohertz to 2000 kilohertz, and the motions of as small as 10 power minus 12 inches and less can be detected. So these sensors can hear breaking of a single grain in a metal, a single fiber in the fiber reinforced composites, and a tiny gas bubbles can be from a pinhole leak as it arrives at the liquid surface. So this sensors is an acoustic emission sensor. It's a transducer. It's almost is a piezoelectric crystal, which is commonly made of a ceramic such as lead synchronate, titanate, P30. So here you have the diagram figure, and this is a casing, and you have a damping material inside, and you have an electrode, the piezoelectric element, and you have a wear plate here, and this sensor, the transducer, is placed above the test specimen, and in between this sensor and the sample, a couplant material is applied. So applications of acoustic emission testing. So weld monitoring. So during the welding process, the temperatures changes induce stress between the weld and the base metal. So this weld can be monitored by using this acoustic emission test. And these stresses, the stresses developed due to welding, are often relieved by heat treating the weld. So next is the bucket truck integrity evaluation. So accidents and then overloads and fatigue can all occur when operating this bucket trucks or other aerial equipments. So that can be detected by this acoustic emission. And if a mechanical or structural defect is ignored, serious injury or fatality can result. So this testing can be all these can be tested using acoustic emission. And bridges, it is used for acoustic emission testing, can be used for testing of the bridges. And this bridges, most of the bridges contains many welds, joints and connections, and the combination of load and environmental factors which influence damage the mechanisms, and maybe due to corrosion. So this all these defects can be tested using acoustic emission. And for monitoring of the bridge, you can use this test. Any damages, any defects, bridge without requiring bridge shutdown, you can use this acoustic emission test. And traffic flow is commonly used to load or stress the bridge for the acoustic emission testing. So application of acoustic emission testing is used. This testing is mostly used in aerospace structures, and complex assemblies of components which have been designed to carry significant loads as light as possible can be tested using this acoustic emission technique. And in laboratory structural test as well as in flight test applications, you can use this test. And this NASA's Wing Leading Edge Impact Detection System is based on this acoustic emission technology. So other applications involves this acoustic emission techniques. It's used in petrochemical and chemical for storage tank, reactor vessels, offshore platform, drill pipes, pipeline walls, hydro treater, etc. And electric utilities like nuclear reactor vessels, piping, steam generators, ceramic insulators, transformers, and aerial devices are tested using this acoustic emission. Fiber reinforced polymer matrix composites, in particularly like this glass fiber reinforced parts or structures, examples, the fan blades are being tested using this acoustic emission testing. And for research of materials, example for this material property investigation and breakdown mechanisms, and you can use this acoustic emission testing. And for performing this real-time leakage test, it is a location within various components, the small valves, steam lines, tank bottoms, and go for this acoustic emission testing. So it has its own advantages. This test is very high sensitive. Early and rapid detection of defects, flaws, cracks, etc. can be done. And it's for real-time monitoring. Cost is reduced. And minimization of planned downtime for inspection. No need for scanning the whole structural surface. So that is advantage. And it also has its limitations. It's poor repeatability and influence of ambient noise and attenuation of signals would result in a poor result output. And data processing is sophisticated. Acoustic emission results are set firmly to the knowledge and experience of the service provider. So with this, we come to an end to this session. So thank you and have a great day.